In this video, we will be talking about what a titration is and reviewing some math associated with titrations to prepare you for a lab that we will be doing in class in the near future. In a titration, we add a chemical of a known concentration, which is called the titrant, and we slowly add that to a chemical of unknown concentration, which is called the analyte. And our goal in a titration is to determine the unknown concentration of the analyte. We call it an analyte because that's the chemical whose concentration we are going to analyze. You want to be familiar with some of the equipment that we use in a titration. So if you look over at the diagram to the side, you'll notice a burette. We have looked at those in class before, and we'll review what they are and how they work a little bit more later in the video. You'll see burette spelled B-U-R-E-T or B-U-R-E-T-T-E. I've seen both spellings. The burette is a tall, long, skinny chemical container that has a valve here on the bottom. That valve allows us to slowly dispense one chemical into another, and sometimes as slow as 1 or 2 drops at a time. In our titration that we are going to be doing in the lab, our titrant is going to be sodium hydroxide. So we always put the titrant in the burette, and in our case, we're going to have sodium hydroxide in one of our burettes. Below the burette, you will see an Erlenmeyer flask, and we're going to start with a known volume of our analyte down in there. So we won't be adding any more analyte unless you pass the end point. More about that in a second. Our analyte in our lab is going to be vinegar because we do not know the concentration of vinegar. We are going to be trying to determine that in our reaction. And we are always in a titration seeking what's called the equivalence point. At the equivalence point, the moles of the analyte that we are at, that we have in the flask below, that we're trying to analyze, is the point where the moles of analyte are equal to the moles of titrant that we have added. So we don't know how many moles of analyte that we have in, but if we slowly add titrant until we get to something that indicates we're at this special equivalence point, then we will know that the moles of titrant are equal to the moles of analyte. And what we often do, and what we will be doing in this titration, is using an indicator to detect the end point. The end point is the point where an indicator changes color. And we are going to use an indicator called phenolphthalein, and that indicator is clear in the presence of acids and pink in the presence of bases. So in our container, we will start with our vinegar, which is an acid down here, so our indicator will be clear. And when we get enough titrant, NaOH added, that we get to the end point, we're going to be looking for a very pale pink color. That pale pink is the indication that we have reached our endpoint, so that our moles of vinegar in the container are equal to our moles of sodium hydroxide that have been added from the burette. The math that you're going to see in this video is all just really a review of stoichiometry. Titrations are just a specific application of stoichiometry. At the beginning of the year, when we learned how to record measurements, we looked at how to read a measurement from a burette, and you had to practice this on your very first test of the year, but it has been a while since we've needed to look at one. So first, I want to remind you that when we use a burette, that's that long, skinny tube with the valve at the bottom, that the purpose of the burette is not to tell us how much liquid is in the burette, rather it shows or measures how much liquid has been dispensed from the burette into another container. So it measures how much liquid has been dispensed. That means when a burette is full, the reading at the top of the burette is actually 0.00 milliliters, because when the burette is full, no liquid has yet been dispensed from it into another container. I want to look at this zoomed in meniscus here. First good tip of measurement is to remind ourselves we always measure the bottom of the meniscus, the bottom of that little dip that's made by water. The second thing to notice and remind ourselves of is the fact that burettes, because they measure how much has been dispensed, they read in reverse order. So it's 28 and then 29 and then 30. So students are tempted to call this measurement like 29.1. That is wrong, because this measurement, this bottom of the meniscus, falls between the 29 and the 28 line. So in reality, we're recording our measurement from the top down. This line here represents 28.5, 28.6, 28.7, 28.8, and 28.9. In good measurements, if the instrument is marked to the tenths place, as this one is, we need to record our measurement to the hundredths place, 1 decimal place past that. This measurement falls between 28.8 and 28.9, but closer to 28.9. So students tend, possible estimation on that last decimal place, 28.86 milliliters, 28.87 milliliters, 28.88 milliliters. That last decimal place can vary a little bit, but these would all be reasonable values to record for the measurement of this liquid in our burette. To demonstrate my point, we're going to do a calculation, an example acid-base titration question here, and you're going to see it looks just like the titration problems that we did just a chapter or two ago. So we're going to titrate hydrochloric acid with sodium hydroxide. So hydrochloric acid, in this case, that's going to be our analyte, because we're saying that it's being titrated by, and our titrant, the thing doing the titrating, is going to be sodium hydroxide. So it sounds like when the color change happened in this particular experience, that 19.3 milliliters of sodium hydroxide had been dripped from the burette down into the flask of hydrochloric acid below, and saying that it reached the end point, that's saying that the color change happened, and it's telling us that moles of titrant and moles of analyte have to be equal. The first, I just want to consider the reaction that's going to happen. We've got hydrochloric acid reacting with sodium hydroxide, and we will get sodium chloride and H2O as our products. In this reaction, and in every acid-base reaction, since acid-base chemistry is concerned with the transfer of a single H+, we're always going to have coefficients in acid-base titrations of 1 to 1, which makes our work a little bit easier. So when I look at what I know and I think about stoichiometry, we've got several numbers here, but I want to start with the chemical that I know the most about. We know both the molarity and the volume for sodium hydroxide. We only know the volume for hydrochloric acid. So I'm going to start with the chemical I know the most about, which is the sodium hydroxide. We have 19.3 milliliters, but that's equivalent to, I got to change this to liters to use this with molarity. So it's 0.193 liters. And the molarity is 0.2. That means there are 0.20 moles in every 1 liter. So if we multiply the volume in liters times the molarity, we will get the number of moles that have been added. I got 0.00392 moles of NaOH. And since this is a 1-to-1 ratio, and we're thinking about stoichiometry, didn't ask us anything about our products. We just want to know the moles of acid and base that have been used. Since we know we're at the end point, the moles of acid and base that have been used are the same. And we're going to assume that we have used up exactly the right amount that's really when we use our indicator and we see this color change, that color change is really telling us this important fact, that the moles of titrant and moles of analyte are perfectly used up. We have no excess and no limiting reactant, just the right amount of both. So now we're going to deal with the HCl. Now we know that we have 0.00392 moles of HCl. And we were, in this case, given the volume of HCl, and we want to know the molarity. So moles divided by liters will give us moles over liters, which is molarity. Sorry, I accidentally put a multiplied sign I didn't need. So if I take moles divided by liters, that will give me the molarity of my HCl, which I found to be 0.0784 molar HCl. And that is the concentration of the HCl. We have answered our question. Hopefully you see that it's very similar to our use of molarity from a previous chapter. Earlier in the unit, I did a demonstration of a titration using a LabQuest and a drop counter that automatically graphed the hydronium concentration as a function of volume of titrant added from the burette. And we got a graph that looks something like, let me slide this over, something like this. We saw that as we slowly added base, and it should have made sense, the hydronium or hydrogen ion concentration went down as the volume of base added went up. And that made sense because as we added base, there's less hydronium, the pH is going up. So we said we thought the hydronium concentration would go down over time. Now, what's called the titration curve, what you more often look at, we take this hydronium concentration and we convert it to pH, because most things in acid-base chemistry, people don't like 10 to a negative exponent, so we look at the pH more often. So if we take this graph and we kind of transform it here, so that instead of putting the hydronium concentration on the y-axis, we instead put the pH on the y-axis, and that pH we just get by doing negative log of the hydronium or hydrogen concentration. Then we get a graph that looks more like this. This actually was just me doing this with one of the class's data. When you look at the graph, the most important point to recognize on a titration curve is this point right here. This is what that equivalence point or the end point looks like on the titration curve. That point where the moles of titrant and moles of analyte are equal. So you get a very vertical part on the graph, and the very middle of that vertical part, that's where the equivalence point is, and that's what an equivalence point looks like on the titration graph. Before the equivalence point, we've got a really low pH, and that's where we have mostly acid in our solution. Past the equivalence point here, now we've got a really high pH. That's where now we just keep adding extra base, and it's right there in the middle of that vertical section where the moles of acid and moles of base are equal. On the previous slide, we looked at a titration curve for an acid titrated by a base. So the pH started low and ended high. Now we're going to sketch and predict what a titration curve would look like if we started with sodium hydroxide, a base. So that means that my base would be my analyte, and it would be in the flask that we're measuring the pH of. And we're going to titrate that base with a strong acid such as hydrochloric acid. So our titrant this time is going to be acid, the thing that we're slowly adding. So the pH, it says sketch the shape of the titration curve you would expect to obtain. Since we are starting with a base as our analyte, the base is the thing that we're measuring the pH of. In this case, the pH is going to start high and it's going to end low somewhere over here. But the shape, the general shape of the titration curve is going to be very similar, where it's kind of level, flattish at the beginning and the end, and there's a very steep part in the middle. And I'm going to go ahead and label one other point here this point pH of 7, because if it makes sense to you, at the equivalence point, the pH is going to be about 7 because we have equal moles of acid and base. So level at the beginning, vertical in the middle, level again at the end. That's roughly what a pH curve would look like for a base titrated by an acid instead of an acid titrated by a base. Now we're going to think about how would this graph look different if the hydrochloric acid I used was twice as concentrated as the previous question. So think about what that means. We're now adding acid that for every milliliter that we have, we get twice as many moles of acid. So in our original sketch here, we show, I just picked an arbitrary amount, but I said, say we use 5 milliliters of acid. Now the acid we're using gives twice as many moles per milliliter or per liter. So instead of using 5 milliliters to get to the equivalence point, we would only need half as many, or say for sake of argument, 2.5 milliliters of acid to get to the equivalence point. So since there's twice as much acid in every milliliter, we need half as many milliliters of acid to get to the same point. But the curve has the same general shape, kind of flat at the beginning, vertical part in the middle, and then it flattens out again at the end. And we still start with a high pH because we start with our base in our bottom container, and it's our analyte, and the pH is going to be low at the end because our titrant that we are adding as time goes on in this example is hydrochloric acid. Now it's your turn to do a little bit of practice.